Okay, continuing where we left off. I think we already did this in the last video. However, to recap, how do you determine polarity in the following molecules? So like this is two nitrogens, so the bond is nonpolar, therefore the molecule is nonpolar. Now CH, Cl3 and CCl4. If you compare CCl4, you can see that the dipoles are cancelling because it's a symmetrical molecule. Now if you take out this Cl and introduce an H, you create an asymmetry. That means there's no more this dipole. CH bond is nonpolar. Therefore, that asymmetry makes the CHCl3 polar, all right, because there is a net dipole, the dipoles are not cancelling, all right, there's nothing to cancel this dipole out, okay. In NF3, that's kind of like ammonia, and you see how the dipoles are directed towards nitrogen. Here the dipoles are directed towards fluorine because the fluorines are more electronegative. Fluorine has an electronegativity value of 4, and so it's pretty high, so it's directed away from nitrogen to the fluorine. And again we see that the dipoles are not cancelling, it's asymmetrical, and so this is definitely polar. CCl4 is non-polar, the dipoles are cancelling. CH3OH looks like this, the structure, and you can see that the dipoles are directed towards oxygen, they're not cancelling. So CH3OH, methanol, is polar. I2, just like N2, the same atoms making up the molecule, and so the bonds are nonpolar, the molecule is nonpolar. C2F2. Now fluorine is very polar, all right. So there are two dipoles, one directed towards this fluorine and the other one directed towards the other fluorine, and of the same magnitude, and they cancel each other out. CO, there is one dipole directed towards oxygen and a single dipole is not cancelled out, and therefore CO is polar. Okay. All right, so N2 nonpolar, CHCl3 chloroform polar, NF3 is polar, CCl4 nonpolar, methanol, CH3OH polar, I2 nonpolar, C2F2 is nonpolar, and then CO is polar. All right, the last section is the attractive forces in compounds. And here we see a protein structure, a 3D protein structure, and different types of attractive forces like ionic bonds and hydrogen bonds. So we look in detail at the different types of attractions. So dipole-dipole attraction. So as you can see here, there are two HCl molecules. Because of the electronegativity difference between hydrogen and chlorine, there is a charge separation and there's a dipole, and chlorine has a partial negative charge. Now an adjacent molecule of hydrogen chloride, the hydrogen, which is partially positive, is going to get attracted to the chlorine, which is electron dense, all right. So there is going to be the unlike charges attract, so there is going to be a force of attraction between this chlorine and the other hydrogen. So this continues, it forms like a chain, a network, and these are called as dipole-dipole attractions. And so this is between the molecules, intermolecular attractions, all right. Now you have ammonia, which also has an electronegativity difference between the nitrogen and hydrogen, and that creates a charge separation. And again, this hydrogen is going to be attracted to the adjacent nitrogen of the adjacent molecule because of the opposite charges. So this is a kind of dipole-dipole attraction. However, because hydrogen is involved, it is called as a hydrogen bond, all right. So you see hydrogen bonds developing in molecules where there is either nitrogen directly attached to a hydrogen or oxygen directly attached to a hydrogen, or fluorine directly attached to a hydrogen. All right, so the Von rule. All right, so if you have molecules which contain fluorine, oxygen, or nitrogen, you see the presence of hydrogen bonds. Hydrogen bonds are very strong, and they are instrumental in maintaining the shape of DNA. They are also pretty strong in protein structure as well. All right, dispersion forces. Now you see this mostly in non-polar molecules. What happens is there is a shift in electron density. All right, so there's a sudden shift in electron density, and the electrons start moving and accumulating in one area. And because electrons are very negative, they carry the negative charge with them. So that area becomes slightly negative, partially negative. So the area that is deprived of electron becomes positive because of the presence of that nucleus. All right. So this leads to the formation of a temporary dipole. Now this temporary dipole will induce the neighboring molecule also to form a temporary dipole. All right. So this leads to, again, like a chain reaction, a lot of induced dipoles. And this is a weak type of interaction, and it's called as dispersion forces. All right. So because of this weak dispersion forces, non-polar molecules are able to form liquids and solids because that binds them together, these weak dispersion forces. All right, how is the strength of the attractive forces in melting and boiling points related? If you have very strong attractive forces, like in ionic compounds, melting points are very high. All right, because the ionic force of attraction is extremely strong. All right, so between the metal ion and the non-metal ion, it's a very strong attraction, it's a very strong bond, therefore, and therefore to break it requires a lot of investment of energy. So ionic compounds have high melting points. So even table salt, just to melt 1 grain of salt would require a temperature of 801 degrees centigrade. All right, so they have high melting points. And also molecules that have hydrogen bonding, because hydrogen bonding is also very strong, therefore those molecules would have high melting points as well. Okay, so here you see a listing of different types of compounds and molecules. When you have metal and non-metal, they're ionic compounds, and you can see that because ionic bonds are the strongest bond, you can see that the melting points are very high. All right, if you have non-metal compounds, covalent compounds, then the criteria is, do they have hydrogen bonds in them, the Von rule. All right, whenever you have a hydrogen attached to an oxygen, or hydrogen attached to a nitrogen, or hydrogen attached to fluorine, then of course the melting points are going to be high. So water, the reason why it has such a high melting point among liquids and the non-metallic covalent compounds is because of a lot of hydrogen bonds. So to melt water takes a lot of energy. All right, melt ice takes a lot of energy because you have to break up all that network of hydrogen bonds. All right, similarly ammonia has a high melting point among other covalent compounds. Now HCl and HBr, you can't apply the Von rule because there's no oxygen, nitrogen, or fluorine. So it's a dipole-dipole attraction, and so again it's stronger compared to dispersion, so their melting points are a little bit higher compared to non-polar molecules which just have dispersion forces. So if you look at the strengths of bonds, if it is within the atoms and ions, within the molecule, the intramolecular forces, intra, so within, so that's ionic or covalent bonds. Ionic bond is much stronger than the covalent bond in terms of strength, right? Between molecules, the intermolecular forces of attraction, hydrogen bond is the strongest, all right, followed by dipole-dipole, and then last is dispersion. Dispersion forces are the weakest among intermolecular forces. Okay, identify the main type of attractive forces that are present in the following compounds. So NCl3, that would be dipole-dipole. H2O has hydrogen bonds, Von rule. Br2 is going to be dispersion, nonpolar. KCl is going to be ionic, and then ammonia is going to be hydrogen bonds. And I stand corrected, NCl3 is dispersion forces and not dipole-dipole. All right, proteins are important. They are the important biomolecules, make up all the components such as bones, cartilages. They are important because most enzymes are proteins. They also are transport proteins like myoglobin and hemoglobin. So the protein structure is made up of the building blocks called as amino acids. Amino acids contains these kinds of atoms or groups, like the amino group, which is derived from ammonia. There is a central carbon atom called as the alpha carbon, to which is attached the C double bond O and a O group. It's called the carboxylate group, and then the alpha hydrogen. And then it has an R group. This is unique for each of the 20 amino acids because they vary. It could be the R group, could be either a hydrogen or methyl group as it's seen here, and dependent on the R group, the interactions and the properties differ for the amino acids. Okay, so sometimes the R group is this kind of group called the amide group, or it's an OH, or it's the COOH carboxyl group, or it's an NH2 or an NH3 ammonium amine type of group. And again, because of that, their interactions will vary, their properties will vary. Okay. So what happens when proteins are formed is, if you see these two amino acids, they interact with each other, react with each other, and a water molecule gets lost in the process, and then the CO and this NH come and link up. So this kind of bond is called as the amide bond. So proteins are made up of amino acids linked up by this amide bonds. Okay, this type of reaction is called as a condensation reaction. Now, proteins have different levels of structure. This is called as a secondary structure of protein, and one of the most important interactions here is the hydrogen bond interactions between the CO of an amino acid and the NH of a different amino acid. All right, so this helical structure is held together by the amino acid the hydrogen bond interactions. So hydrogen bonds can even form between what are called the R groups, the side chains, and also hydrogen bonds can form with the water surrounding the protein environment, and so on. All right, homework on page 189, 191, 195, 200, 203, 209, 212, 218, and 222. At a minimum, try to do at least the odd numbered problems. All right, so this ends this chapter 6.